Hey, I'm Liam, and in front of me here I have the first major steps towards completing this successive approximation register analog to digital converter. Here we have the digital to analog converter, which is an R2R DAC right there. And then over here with these two ICs, we have the comparator and the sample and hold circuit. I'll go into a little demonstration first, and then we'll go in and explain how everything here works. So to begin with, this chip right here is the sample and hold chip. What it does is it takes the sample voltage reading that the ADC is going to convert, and it holds it for the duration of the conversion. This is because you don't want your reading to change on you while you're trying to approximate it, because then you'd get all sorts of bad numbers. So let's go into a little bit about how this sample and hold chip works. Okay, so in this setup here, we currently have the output of the sample and hold chip being read on this DMM. And what happens is the sample and hold chip samples the reading from this potentiometer as I turn it. But you can see that as I turn it, the reading doesn't change. And that's because pin 8 on the sample and hold chip, which is the logic pin, enables the sample. So here I can go ahead and I can press that, and you can see that the value within the sample and hold chip updates right away as soon as you press it. And then when you let go, you'll get a slow discharge. Okay, so now I've reconnected some stuff, and now we're reading the output of the DAC, which are these resistors over here on the side. I'm going to go back to the voltage reading here because that's what's more important. And we're going to talk about how we can use the DAC to create some analog voltage values. So now with the whole DAC in view, we can talk a bit about how that works. So this is a 7-bit DAC, meaning that each of these 7 resistors in the back are each 1 bit. And together they make up a binary number that is represented as a voltage. The supply voltage here is 9 volts, which means that we have 128 increments within this 9 volt range that we can set the DAC to. So right now, with it being 4.5 volts roughly, that means that the first bit, or the most significant bit on the DAC, is set, and that's true. Right now, this red LED is on, which means that the DAC output is currently higher than the sample output. So let's go along and find out what the DAC should be set up and mimic the successive approximation that we'll eventually do with the full circuit. Okay, so there we have it. We successfully turned off the LED in the least number of off states on the DAC as possible, meaning that we found the best binary approximation for this analog reading. So let's go ahead and actually take a look at what we're reading on the sample and hold chip. We can see over to the side that the DAC is currently reading 2.28 volts, and the actual voltage that we're trying to get is 2.23 volts. So we did get pretty close. Let's take a look at how sample and hold circuits work. Alright, so here on screen is a sample and hold circuit that I designed for this project. This is not the sample and hold circuit within the LF398 because I think that sample and hold circuit is more complicated than is necessary to still learn a lot about how they work. I also made some changes. I decided to make my sample and hold circuit edge triggered because I was kind of building this and wondering why the other one wasn't edge triggered. It seemed kind of strange that it was triggered for the whole high duration. Anyways, let's get on to how this works. So to start off, we have the switch. The switch is mimicking pin 8, or the logic pin, on the LF398, and you can see that when you flip the switch, the circuit updates and the sample voltage is held. This edge detection circuit is quite simple. It works by simply allowing current to pass through it while a capacitor is charging, but since the capacitor is quite small, it doesn't take that long to charge, and therefore you only have a very short pulse duration when you actually have a signal going through, and that's pretty much your rising edge. Once the edge detection is done, we see that the next thing is an NPN transistor. This transistor simply allows voltage from the input voltage, the sample voltage, to go to the hold capacitor, which is that 100 nanofarad capacitor. You can see it goes through a 1 ohm resistor, but this is simply because Falstad won't allow you to just charge capacitors with zero resistance because there is an infinite amount of current for some time. When this transistor is turned on, we allow the sample voltage to go into the hold capacitor, which charges up to the same level as the sample voltage. And after that edge is over that we talked about previously, the transistor will turn off and the capacitor will be left at the voltage that it was charged to. If left alone, this capacitor would store the sample voltage forever. However, the problem with this is that if we were to try and measure the sample voltage or try and run something off of it, any type of load would inherently change the sample voltage because we would have to draw some energy to be able to read it or use it or do anything else. So instead, we make a trade-off where we put it through a comparator with feedback that will keep the sample voltage steady, however, at the cost of a very minimal voltage leak, as the comparator, while it has a high impedance input, it does not have an infinitely high impedance input and will draw some current and thus voltage out of the hold capacitor, meaning that the voltage will go down over time. On the output of this comparator is the hold voltage of the circuit, is the hold voltage that's presented to the rest of the circuit, which will not go down when you draw current from it, but will leak over time, as I just mentioned. So in essence, that's how a sample and hold circuit works. And with that, that's about it. Thanks for watching.